This video is about interference of light, where the optical interference is discussed without formula and equations. That is, we have the eagle's eye view over this wonderful topic. An important characteristic of light waves is their ability under certain circumstances to interfere with one another, obeying the principle of superposition. Most of us observe some form of optical interference every day, but usually do not realize the events in play behind the often kaleidoscopic display of color produced when light waves interfere with each other. One of the best examples of interference is demonstrated by light reflected from an oil film floating on water. Another example is a soap bubble that reflects a variety of beautiful colors when illuminated by light sources. The formation of an image in an optical instrument, like a microscope, relies on the complex interplay between two critical optical phenomena: interference and diffraction. Light passing through the specimen is scattered and diffracted into divergent waves by tiny details and features present in the specimen. Some of the divergent light scattered by the specimen is captured by the objective and focused onto the intermediate image plane, where the superimposed light waves are recombined or added by the process of interference to produce a magnified image of the specimen. The seemingly close relationship between diffraction and interference occurs because they are manifestations of the same physical process and produce apparently reciprocal effects. One of the best examples of interference is demonstrated by light reflected from a film of oil floating on water. Another example is a thin film of a soap bubble which reflects a spectrum of beautiful colors when illuminated by natural or artificial light. The dynamic interplay of colors in a soap bubble derives from simultaneous reflection of light from both the inside and outside surfaces of exceedingly thin film of soap whose thickness is of the order of microns. The light reflected from the inner surface of the soap film interferes both constructively and destructively with light reflected from the outer surface. The interference effect is observed because light reflected from the inner surface of the bubble must travel farther than light reflected from the outer surface. This is known as path difference between the two reflected light. The variations in the thickness of soap film produce corresponding path differences for light waves which they must travel to reach our eyes. When the waves reflected from the inner and outer surface of the soap film recombine, they will interfere with each other to either remove or reinforce some wavelengths of white light by destructive or constructive interference. The result is a dazzling display of color that seems to gyrate along the surface of the bubble as it expands and contracts with wind currents. Simply turning the soap bubble or moving it closer or farther away causes the colors to change or even disappear altogether. If the extra distance traveled by the light waves reflected from the inner surface is exactly equal to the integral multiple of wavelength of those bouncing away from the surface, then the light waves will combine constructively to form bright colors. In areas where the waves are out of phase with each other, even by some fractional portion of wavelength, destructive interference effects will begin to occur, attenuating or cancelling the reflected light and hence the color. In this case, the path difference between the waves will be odd multiple of half wavelength. Music, movie and computer enthusiasts are also exposed to the interference phenomenon each time they load a compact disc into the audio player or a CD-ROM drive. The closely spaced spiral tracks on a compact or digital video disc contain a series of pits and lands that are utilized to encode the digital profile of the audio and or with the video sequences contained on the disc. The very close spacing of these tracks mimics the ultra-fine lines present on a diffraction grating to produce a spectacular rainbow-like effect of color when ordinary white light is reflected from the surface. Like the soap bubble, the color is derived from the interference between the reflected light waves bouncing from the neighboring tracks on the disc. Interference is responsible for the often brilliant iridescent coloring displayed by hummingbirds, a variety of beetles, and other insects whose wings cast a metallic luster, and several species of magnificent butterflies. For example, the wings of the diamond beetle are covered with a microscopic crisscrossed diffraction grating having approximately 2000 lines per inch. White light reflected from the wings of the beetle produces a stunning spectral display of interference pattern like that originating from the source of a compact disc. A similar effect is created by the tortoise beetle, which has wing casings composed of multiple chitin layers, rendering them iridescent in the reflected light. Interestingly, this insect can vary the moisture content of the thin films to produce thickness variations, changing the predominant reflected interference color from the gold to reddish copper. Another spectacular example of naturally occurring interference, the Morphodidis butterfly, thrives in the Amazon rainforest and exhibits one of the most beautiful form of iridescence seen in the insect world. The intense blue wing color is a consequence of color producing structures fastened to the scales layering the butterfly's wings. Each scale is composed of two sheet-like extremely thin lamella, an upper and lower, which are separated by a void held apart with vertical roots. The lamellae support an even smaller network of Christmas tree shaped ridges containing plates or branches projecting laterally from a central stalk. Plates on the ridges arising from thin layers of chitin that are separated by air spaces at distances equal to 1/2 of the wavelength of blue light mimic a natural diffraction grating. The ridges have evolved with spacings at the correct intervals for light waves reflecting from the plates to undergo constructive and destructive interference. The result is a deep iridescent blue color that covers almost the entire wing structure, although no blue light is actually reflected from the wing scales. The classical method of describing interference includes presentations that depict the graphical recombination of two or more sinusoidal light waves in a plot of amplitude, wavelength, and relative phase displacement. In effect, when the two waves are added together, the resulting wave has an amplitude value that is either increased through constructive interference or diminished through destructive interference. To illustrate the effect, consider a pair of light waves from the same source that are coherent, that is having an ideal phase relationship, and traveling together in parallel direction. If the vibrations produced by the electric field vector from each waves are parallel to each other, then the light waves may combine and undergo interference. In addition, the waves all have the same wavelength and are coherent but vary with respect to amplitude. Assuming all of these criteria are met, then the waves can interfere either constructively or destructively to produce a resultant wave that has either increased or decreased amplitude. If the crest of one of the waves coincide with the crest of the other, the amplitudes are determined by the arithmetic sum of the amplitudes from the two original waves. For example, if the amplitudes of both the waves are equal, the resultant amplitude is doubled. Also, note that light intensity varies directly as the square of the amplitude. Thus, if the amplitude is doubled, intensity is quadrupled. Such additive interference is called constructive interference and results in a new wave having increased amplitude. If the crest of one of the waves coincides with the trough of the other wave, in effect the waves are out of phase by 180 degrees or pi radian, or half a wavelength out of phase with each other, the resultant amplitude is decreased or may even be completely cancelled. This is termed as destructive interference and generally results in a decrease of amplitude or intensity. In case where the amplitudes are equal but 180 degree out of phase, the waves eliminate each other to produce a total lack of color or blackness. Real-world interference phenomena are not as clearly defined as the simple case presented in the illustrations. For example, The large spectrum of color exhibited by a soap bubble results from both constructive and destructive interference of light waves that vary in amplitude, wavelength, and relative phase displacement. A combination of waves having amplitudes that are approximately equal but with different wavelengths and phases can produce a wide spectrum of resultant colors and amplitudes. In addition, when the two waves of equal amplitude and wavelength that are 180 degrees or half a wavelength out of phase with each other meet, they are not actually destroyed. All the photon energy present in these waves must somehow be recovered or redistributed in a new direction according to the law of conservation, as we know that photons are not capable of self-annihilation. Instead, upon meeting, the photons are redistributed to the region that permit constructive interference, so the effect should be considered as a redistribution of light waves and photon energy rather than spontaneous construction or deconstruction of light. Therefore, simple diagrams representing constructive and destructive interference should only be considered as tools that assist with the calculation of light energy traveling in a specific direction. Young's double slit experiment. Among the pioneers in early physics was a 19th century English scientist named Thomas Young, who convincingly demonstrated the wave-like character of light through the phenomenon of interference using diffraction techniques. Young's experiment provided evidence in contrast to the popular scientific opinion of the period, which was based on Newton's corpuscular theory for the nature of light. In addition, he is also responsible for the concluding that different colors of light are made from waves having different lengths, and that any color can be obtained by mixing together various quantities of light from only three primary colors: red, green, and blue. In 1801, Young conducted a classical and often cited double slit experiment, providing important evidence that visible light has wave-like characteristics. His experiment was based on the hypothesis that if light were wave-like in nature, then it should behave in a manner similar to ripples or waves on a pond of water. Where opposing waves meet, they should react in a specific manner to either reinforce or destroy each other. If the two waves are in phase, that is the crust, meet, then they should combine to make a larger wave. In contrast, when the two waves meet are out of phase, that is the crust of one of the waves meets with the trough of the other, the waves should cancel and produce a flat surface in that area. To test his hypothesis, Young devised an ingenious experiment. Using sunlight diffracted through a small slit as a source of semi-coherent illumination, he projected the light rays emanating from the slit onto another screen containing two slits placed side by side. Light passing through the slits was then allowed to fall onto a third screen, the detector. Young observed that when the width of the slits were large, spaced far apart, and close to the detection screen, then two overlapping patches of light formed on the screen. However, when you reduced the size of the slits and brought them closer together, the light passing through the slits onto the screen produced distinct bands of colors separated by dark regions in a serial order. Young coined the term interference fringes to describe the bands and realized that these colored bands could only be produced if light were acting like a wave. The basic setup of the experiment is represented here. Red filtered light derived from the sunlight is first passed through a slit to achieve a semi-coherent state. Light waves exiting the first slit are then made incident on a pair of slits positioned close together on a second barrier. A detector screen is placed in the region behind the slits to capture overlapped light rays that have passed through the twin slits, and a pattern of bright red and dark interference bands become visible on the screen. The key to this type of experiment is the mutual coherence of light diffracted from the two slits at the barrier. Although Young achieved his coherence through the diffraction of sunlight from the first slit, any source of coherent light, such as laser, can be substituted for light passing through the single slit. The coherent wavefront of light impacting on the twin slits is divided into two new wavefronts that are perfectly in phase with each other. Light waves from each of the slits must travel an equal distance to reach a point A on the screen, and should reach that point still in phase or with the same phase difference. Because the two waves reaching point A possess the necessary requirements for constructive interference. They should act together to produce a bright red interference fringe on the screen. In contrast, neither of the points B on the screen is positioned equidistant from the two slits, so light must travel a greater distance from the one slit to reach point B than from the other. The wave emanating from the slit closer to point does not have as far to travel to reach its destination, as does a wave traveling from the other slit. Consequently, the wave from the closest slit should arrive at point B slightly ahead of the wave from the farthest slit. Because these waves will not arrive at point B in phase, they will undergo destructive interference to produce a dark region, that is, interference fringe on the screen. Interference fringe patterns are not restricted to experiments having the double slit configuration, but can be produced by any event that results in the splitting of light into waves that can be cancelled or added together. The success of Young's experiment was strong testimony in favor of the wave theory, but was not immediately accepted by his peers. The events in place behind phenomenon such as the rainbow of color observed in soap bubbles and Newton's rings, although explained by his work, were not immediately obvious to those scientists who firmly believed the corpuscular theory of light. Other types of experiments were later devised and conducted to demonstrate the wave-like nature of light and interference effects. Most notable are the single mirror experiment of Humphrey Lloyd and the double mirror and biprism experiments devised by Augustin Fresnel for polarized light in uniaxial birefringent crystals. Fresnel concluded that interference between beams of polarized light could only be obtained with beams having the same polarization direction. In effect, polarized light waves having their vibration directions oriented parallel to each other can combine to produce interference, whereas those that are perpendicular do not interfere. Newton's rings experiment. Sir Isaac Newton, the famous 17th century English mathematician and physicist, was one of the first scientists to study interference phenomena. He was curious about how the brilliant display of color on the surfaces of soap bubbles arose, especially considering the bubbles were composed of a colorless liquid soap solution. Newton correctly speculated that the color might be attributed to the close proximity of the inner and outer surfaces of the bubbles, and devised an experimental approach designed to mimic the colored patterns observed. In this famous Newton's rings experiment, Newton placed a convex lens having a large radius of curvature on a flat glass plate and applied pressure through a brass frame to hold the lens and glass plate together, but still separated by a very thin void filled with air and having the same dimensions as visible light. When he viewed the plates by reflected sunlight, he observed a series of concentric bands having both light and colored regions. The orderly progression of the rings surprised Newton. Near the center of the point of contact, the rings were larger and had colored patterns starting with the black, then progressing through the faint blue, white, orange, red, purple, blue, green and yellow. The bands had greater intensity and were thicker at the center, grew thinner as they progressed outward, and finally trailed off at the edges of the brass frame. Newton also discovered that if he illuminated the glass with red light, the colors changed to produce alternating red and black lines. In a similar manner, blue light produced blue and black rings, while green light generated green and black rings. Furthermore, Newton found that spacing between the rings depended upon the color. Blue rings were closer together than green rings, which were closer together than the red rings. An identical effect could be observed for interference fringe spacing in the double slit experiment if different colored filters were employed. Newton recognized that the rings indicated the presence of some degree of periodicity, but was puzzled over the result of the experiment. In fact, the physical basis for the formation of rings became a mystery that endured for over 75 years after Newton's death. It wasn't until Young conducted the double slit experiment that scientists realized the light reflected from the top and bottom surface of the glass becomes superimposed and produces interference pattern that appear as the colored rings. Today, this principle is often used by lens manufacturers to test the uniformity of a large porous surfaces. The experiment can also be used to find the refractive index of a liquid, the thin film between the two glass surfaces. Interference filters. The explosive interest in fluorescence microscopy using classical wide field observation alone or in the combination with scanning, confocal and multiphoton laser techniques has led to the rapid development of new filter technology designed to enable the microscopist to selectively excite fluorophores and observe their secondary fluorescence with a minimum of background noise. For these applications, filters having multiple thin coatings of dielectric materials, commonly termed as interference filters, have become the mechanism of choice for wavelength selection. In general, interference filters are constructed of planar optical glass coated with dielectric materials in layers either 1/2 or 1/4 wavelength thick, which act by selectively blocking and reinforcing the transmission of specific wavelength bands through a combination of constructive and destructive interference. The filters are designed to transmit a limited range of wavelengths that are reinforced through constructive interference between the transmitted and reflected light waves. Wavelengths not selected by the filter do not reinforce each other and are removed by destructive interference or reflected away from the filter. The dielectric materials commonly employed for interference filter are electrically non-conductive metallic salts and true metals having specific refractive index values. Salts such as the zinc sulfide, sodium aluminum fluoride and magnesium fluoride, as well as metals such as aluminum, are several of the materials of choice for designing and building filters of this type. Interference filters, much like the thin chitin structures in iridescent insects or the soap thin films discussed, rely on the physical properties existing at the interface between two very thin dielectric materials of different refractive index to reflect, transmit and promote interference between incident light waves. Wavelength selection is dependent on the dielectric thickness and refractive index of the thin layer coatings used to build the filters. Coatings on the interference filters are fabricated in units termed cavities, with each cavity containing 4 or 5 alternating layers of dielectric salts which are separated from other cavities by a space layer. The number of cavities determines the overall precision of wavelength selection. Filter performance and wavelength selection can be dramatically enhanced by increasing the number of cavities, as exemplified by the current high-performance filters having up to 10-15 cavities and being able to produce bandwidths of a single wavelength. These extremely selective filters have stimulated research in the quest for new fluorophore dyes and have dramatically boosted the search for mutation variations of the popular biologically active green fluorescent protein. Anti-reflection coatings. Thin film anti-reflection coatings greatly reduce the light loss in multi-element lenses by making use of phase changes and the dependence of reflectivity on index of refraction. A single quarter wavelength coating of optimum index can eliminate reflection at one wavelength. Multi-layer coatings can reduce the loss over the visible spectrum. Destructive interference is exploited in making non-reflective coatings for lenses. The coating material generally has an index of refraction less than that of glass, so both reflected waves have a half wavelength shift. A film thickness of quarter wavelength in the film results in destructive interference. One philosophical note on anti-reflection coating to really make your head spin if it isn't already. In our analysis, we consider the two reflected waves and see how they cancel. This means none of the wave energy is reflected back into the first medium. Where does it go? It must all be transmitted into the third medium, and that is the whole point of a non-reflective coating, to transmit as much as light as possible through a lens or a lens system. So even though we did the analysis by drawing the waves reflecting back, in some sense they really don't reflect back at all, because all the light ends up in the medium 3. Conclusions. In addition to the soap bubbles, beautiful iridescent insects, and the many other examples we discussed, the phenomenon of visible light interference occur quite frequently in nature and is often utilized to man's advantage in a wide variety of applications. For example, the rainbow-like color spectrum observed on the inside of abalone shells is generated by very thin layers of hard mineral termed nacre or mother of pearl. Light reflected from successive layers undergo interference to produce the display of color in a manner similar to that observed from multiple layers of chitin on the exoskeleton of several beetle insects. In the same fashion, silvery scales on some fish produce colored interference pattern due to multiple layers having varying thickness. The iridescent eyes of the peacock feather are another example of the interference in action. Tiny, rod-shaped structures composed of the protein pigment melanin are arranged in an orderly fashion that produces unique interference colors when observed from different angles. In the mineral world, iridescent opal is composed of microscopic silicate spheres that are stacked in regular layers. Each sphere reflects incident light that interferes with the reflected light from neighboring spheres to produce an exquisite array of color that changes as the stone is turned. Significant and very useful application of the interference effect are the measurements made over long distances with precision laser instrumentation. The laser systems can be used to measure very small distances over a range of many kilometers, a task that is accomplished by splitting the laser beam and reflecting it back from adjacent surfaces that are very close together. Upon recombining the separated laser beams, analysis of the resulting interference fringes will yield a remarkably accurate calculation of the distance between the two surfaces. This technique is also commonly utilized in laser guidance systems designed to control the flight path of manned and unmanned aeroplanes, rockets, and bombs. Interference also occurs in other media such as sound waves in air and ripples or waves induced in a standing pool of water. A very concise and easy interference experiment can be performed at home using a sink full of water and 2 pebbles. First, let the water become very still. Then simultaneously drop the pebbles onto the water about 10 to 12 inches apart from a height of about, say, a foot. Just as with the light waves, the 2 pebbles will induce a series of waves in the water emanating in all directions. Waves formed in the area between the points where the marbles entered the water will eventually collide. Where they collide in phase, they will constructively act together to make a bigger wave, and where they collide out of phase, they will destructively cancel each other out. Interference works in many ways to influence the things we see in our everyday lives. The interaction between light waves that are very close together occurs so often that the phenomenon is often taken for granted. However, from its fundamental contributions to the physics of image formation and a myriad of sensational insect disguises to the beautiful color patterns of halos and coronas in atmosphere, interference of light waves helps to bring color to the world around us.